So with much of your lab work, you'll be creating and generating AC, alternating currents and voltages using an electronic signal generator. So you can see here in the diagrams we have function generators and a typical waveform generator. There are several choices and variations in your labs where you'll get to connect to a function generator or a signal generator and create the sinusoidal outputs that you need for those types of products. So the signal generator is an instrument that electronically produces sine waves for use in testing and controlling electronic circuits and systems. And you'll remember early on in this section, in the previous videos, that it mentioned that a sinusoid can also be created with a mechanical device, a generator. So this is the electronic wave. There are a variety of signal generators ranging from special purpose instruments that produce only one type of waveform in a limited frequency range, up to programmable instruments that produce a wide range of frequencies and a variety of waveforms. Today, there are devices out there that will create just about any type of non-DC, sinusoidal, or otherwise waveform that you need for any specific circuit. All signal generators consist basically of an oscillator, which is an electronic circuit that produces repetitive waves. All generators have controls for adjusting the amplitude and frequency, and we're going to learn more about that. The function generator and the arbitrary waveform generators are instruments that produce more than one type of waveform. So if you need a sinusoid, if you need a square wave, if you need a sawtooth wave, I mean, there are lots of different waveforms available on these other types. Typical function generators then are shown over here to the right. An arbitrary waveform generator can be used to generate standard signals like sine waves, triangular waves, and pulses, as well as signals with various shapes and characteristics. Okay, waveforms can be defined by mathematical and graphical input. A typical arbitrary waveform generator is shown over here on B. So again, when you get in the lab, check it out. You're going to see different types of waveform and sine wave signal generators in your lab. So there are 5 ways to express the value of a sine wave in terms of its voltage or its current magnitude. We can look at the instantaneous, we can look at the peak, we can look at the peak to peak, the RMS, and the average values. And there is value in each of those. Sometimes you need to know what the peak to peak value is. Sometimes you need to know the RMS or the average value. So we're going to look at each of these and determine how do we get to these and of what use are they. So in the instantaneous value, you're basically plotting points on the waveform. So you have an infinite number of points on this waveform as it's shown down here in A. And you can capture them by looking on the scope if you're using a generator, signal generator, and determine what the voltage is at any point. Up here at V3, it looks like we're just about at V max. We're down here, we're at V0. And you can measure them based upon time. So this illustrates that any point in time on a sine wave, the voltage or current has an instantaneous value. And that you're going to find that there is a reason for needing to know that in making measurements and making determinations, especially when we start dealing with waveforms that we have moved or transposed in time, leading and lagging signals, in phase and out of phase. This instantaneous value then is different at different points along the curve. Instantaneous values are positive during the positive alternation and they're negative during the negative alternation. Instantaneous values of voltage and current then are symbolized by using a lowercase v and a lowercase I. So you notice that everything to this point we've used an uppercase value, and we haven't used anything that indicated that it was with respect to time. Typically, V and I, with values taken with respect to time, will have a subscript associated with it that has a T in parentheses. So you know you have I with respect to time. The curve in part A shows voltage only, but it applies equally for the current when the voltages are replaced with I. So we can see here that they've shown a maximum voltage here, but you notice down here the little v is with respect to time. So this big V is just telling me what the maximum or the minimum value is. It helps with the gradations along the vertical axis. You'll notice on the horizontal axis, everything is little t. So this is typically in seconds. That's not to say it couldn't be also a measure in milliseconds or microseconds. Typically not nanoseconds, but it could happen. So an example of instantaneous values in B then shows where the instantaneous voltages of 3.1 volts at 1 microsecond, 7.07 volts at 2.5 microseconds, 10 volts at 5 microseconds, 0 volts at 10 microseconds, etc. So you could plot those if you needed to for any specific value. So if that's the instantaneous value, any point on the curve itself, on the sine wave, what would be the peak value? Well, the peak value of a sine wave is the value of voltage or current at the positive or negative maximum peak with respect to 0. So you can see this V, capital V sub P, this would be the negative capital V sub P, which is our peak values, okay? So it's typically one or the other, okay? Either the positive alternation or the negative alternation. Since the positive and negative peak values are equal in magnitude, a sine wave is characterized then by a single peak value. So you can see it as plus or minus 10 volts, okay? As illustrated in the diagram, for any given sine wave, the peak value is constant and represented by capital V sub P or capital I sub P. The peak value is also called the amplitude. Okay, so it's not a measurement with any time value, it's just the maximum value. If we look below, we have what's called the peak to peak value. This sine wave is a voltage or current from the positive peak to the negative peak. It's always twice the peak value as expressed in the following equations. Peak to peak voltage or current then is represented by VPP, or V peak to peak, or I peak to peak. And we can see that mathematically V peak to peak is equal to then naturally 2 times the peak value. So what is the RMS value? The RMS value then is what's called the root mean square. So you can see we're implying some mathematical relationship of a square root, the mean or the average, and that value being squared. Most AC voltmeters display an RMS value. So when you pick up a voltmeter in your lab, you can just about be assured that it is measuring an RMS value. It's not an instantaneous value. The 120 volts of your wall socket is considered an RMS value. The RMS value also refers to the effective value of a sinusoidal voltage. That's actually a measure of the heating effect on a sine wave. So what are we talking about? Well, what we'd have to do is we'd have to do a comparison. You can see over here on the right, we've got a sinusoidal source that we're pumping some current through at some voltage level, through some resistor. After a while, if we pump enough current through here, it's going to get hot, and it's converting energy, electrical energy, to thermal energy or heat, and it starts radiating that heat. Okay, so if we looked over here, we would know what the voltage is at the point where this thing started radiating some heat. The next thing we do then is we take that same resistor and put it on a DC source. So this is an AC source, put it on a DC source, and determine what DC voltage then radiates the same amount of heat. So there's our correlation. We're matching the amount of heat. We would have to have some thermal measure between these two to determine what the relationship is between our RMS value and our DC value or AC value. So the RMS value then is a sinusoidal voltage equal to the DC voltage that produces the same amount of heat in a resistance as does the sinusoidal voltage. You're never going to do that, but it's good to understand where this came from and why the procedure has to be understood. We're going to do it mathematically. So the peak value of a sine wave can be converted to its corresponding RMS value using the following relationships derived in Appendix B of your text. So the RMS value is considered to be 70.7% or 0.707 of the peak value. The same thing with the amount of current. I can tell you now that that equals about 45 degrees when we start dealing with phasors. So we're using these formulas. You can also determine the peak value if you know the RMS value. So this is good. When you're using your meter, if the question on an exam or on an analysis asks you for the V peak and you're measuring with a meter that's RMS, well, it's just a simple matter of dividing whatever the RMS voltage is you're measuring by 0.707, and you will end up with a value of 1.414 times the RMS value. We do the same thing for current. If we have a peak-to-peak value, we end up doubling it because we know V peak to peak is twice V peak, so we get 2.828 times the RMS value. So again, write this down, these formulas in your notebook, and keep track of these because you are going to see them again and use them. So the last one then, the average value. The average value is a little more difficult because the average value really takes a quick understanding of calculus, because what we're going to do is we're going to measure the area under the curve. The average value of a sine wave taken over one complete cycle is always zero because the positive values above and below the zero crossing negate each other. So if you took all of the measurements on the positive alternation and you subtracted them from all of the alternations on the bottom, on the negative, you would get zero. So there's got to be some way that I can come up with an average value. Well, there is. We're going to show it mathematically. Again, this is based in calculus, but we're just going to give you the end result here. If you're interested, go out and look online. You will see how it's done using the calculus. So to be useful for certain purposes, such as measuring types of voltage found in power supplies, the average value of a sine wave is defined over only 1/2 of the cycle rather than the other. Because if you try to do it for both positive and negative, it's going to come out to zero. That does no good. The average value then is the total under the curve for half a cycle divided by the distance in radians of the curve along the horizontal axis. The result then, again, look in Appendix B of your text. It's expressed in terms of peak value as shown for both voltage and current. So the average is equal to 2 times the peak divided by pi. This gives us 0.637, okay? In most cases, that's the value you're going to use. That's the product you're going to use. That's your multiplier, 0.637. Same thing is true for current. So if we look over here, they ask us to determine peak-to-peak RMS, and the average for this sine wave. So you can see we have a sine wave. It has a maximum amplitude of 5 volts, and no time is given. So they're not interested in that. So V peak then is listed as 4.5 volts. So if we look here, there the top line is 5, halfway up, 4.5. So that's directly reading from the graph. This is what you will use when you start using oscilloscopes. Peak to peak then is 2 times that value. So all I have to do, I don't have to measure anything, just double it. 4.5 twice gives me 9 volts. The RMS value is a factor of 70.7% or 0.707 times the peak value. That gives me 3.18 volts. The average value then is 0.637 times the peak, which gives me 2.87. So make sure you understand this because you're going to see a lot of this. And again, some meters measure in effective, some meters measure in average values. Oscopes always measure in peak and peak to peak, but sometimes there is a selection on the scope that will allow you to calculate on these new digital scopes, RMS and average. Okay, so let's go ahead and stop here. When we come back, we'll look at the phasor relationships, or the basis for the phasor relationships.